26. In 26, you have the volume of liquid flowing in time t through a pipe of radius r is given by the equation, which is this, where P is the pressure difference between the ends of pipe of length L, and C depends on frictional effects of the liquid. And then you got two constants here. Okay, so the whole story is basically you have a pipe and you've got some liquid flowing. This liquid, you can measure its volume, you can measure how much volume flows per time, you can measure the radius, you can measure the pressure differences between the two ends, because in order to have nothing flowing, you need pressure differences. You can measure the length, and you can measure the drag forces that occurs when the liquid is flowing. So sometimes when you do these questions, you can actually use whatever they written in and actually come to a concept or idea of how the whole system works. Then you have a table with all the information. So A, calculate the value of C. You want to calculate the value of C? Let's make C the subject, so let's just flip these two, and you get C is equal to pi P R4 8L with T over V. Pi here is given already. P here is given to be 2.50 times 10 to the 3. R4 here is given to be 0.75, but it's millimeters, so times 10 to the minus 3. And careful, you need to square this. And then you got 8. Your L here is equal to 0.250 as in meters already, as I base unit, so I'm going to convert that. And V over T in this case is 1.2 times 10 to the minus 6. Okay, so you got all the information you have. This one is calculatable, so you pause this video and you can calculate the value. Once I pause this video, you should have a C of around 1.04 times 10 to the minus 3 units Newton second meter minus 2. Next question, we have to calculate the uncertainty in C. So uncertainty in C is quite easy. We have the equation here already. So we just need to write the uncertainty equation. So delta C over C is equal to pi is uncertainty, A is uncertainty. P, R, L, B, T has uncertainties as seen in the box in the table shown. So it's basically delta P over P plus delta L over L plus delta V over T over V over T plus delta R over R times 4. If you check the videos on the uncertainty, why we're using fraction is because of the fact that all of them have different SI base units, and therefore if all of them have different SI base units, the only way to ensure the units do not clash is to use the fractional form. Okay, so that's why we use the fractional form. But when we have power, again, that is uncertainty equation 3 with power means you do not power the whole uncertainty, you just times by 4 to increase the value. Again, remember uncertainties, our aim is to, basically uncertainties increases. Okay? If you power it, you decrease, which then backfires and is no longer uncertainty. So in this case, delta C is therefore equal to, what's the uncertainty of P? 0.05 over 2.50 plus delta L is 0.001 over 0.250. Delta V and V over T is 0.01 over 1.20 plus delta R 0.01 over 0.75 times 4. Again, remember, we don't need to put any of the millimeters and all those other conversion things because why you cancel out. Okay? For example, if you have R here is 0.01 times 10 to the minus 3, 0.05 times 10 to the minus 3, those 10 to the minus 3 cancel out. So all we need to do is just write all their values in the correct units and you define. This is the uncertainty equation, but they want us to find that for C. So we then multiply this whole thing by 1.04 and 10 to the minus 3. Okay, and then you calculate this, you pause the video, and when you unpause this video, you should have a value of around this, plus minus 0.089 times 10 to the minus 3 Newton second meter squared. How do you know it's correct? Well, the power is the same thing, and this uncertainty is always less than this value here. However, I have a calculator, so if there's any mistakes, feel free to feedback to me, or better yet, just double check everything is correct, and then whatever answer you get, it should be the correct version. Okay? Just in case I do not modify the values. Now, C, state the value of C and its uncertainty to the appropriate number of the figures. So in C, how do we write this? We write this as, let's say, C final will be equal to 1.04 plus minus 0.089 times 10 to the minus 3 Newton second meter minus 2. So this part is there. We put the value again to the uncertainty is there already. But in AS, remember, when it comes to absolute uncertainty, what is absolute uncertainty? It has units. You see something called absolute uncertainty. It's just referring to uncertainty with the original units. Okay? You can compare it with fractional uncertainty. Why is it fractional uncertainty? Because you have this uncertainty where all the units basically cancel off each other. When it comes to AS, your uncertainty should only be one SF. So in this case, this one will be written as 0.09. So times 10 to the minus 3 Newton times 10 minus 2. So this is the first thing you need to check. Once you got 0.009, therefore the decimal place will therefore, this one is 2 decimal places. So it is 0.04 2 dp, therefore correct. So second. Okay? So this is your final result. What do I mean by this? Let's say if AS says please keep your SF to 2SF. So if you keep the 2SF version, what you see is plus minus 0.089. This one is the first component to look at. 3 dp, therefore you rewrite the main value to be 3 dp as well. So 0.4 add 1 0. And then it will be consistent. Remember, there's a different way of writing when you got uncertainty. And the SF is in the uncertainty component, not in this value. This one will have to follow the consistency of the decimal places.